I didn't want to leave our unit on electrostatics and potential without at least a brief introduction to capacitors, because they're so closely related to what we've been discussing, and they're also very, very useful in technology. And without going into detail about that, they're used in radio circuitry and power supplies. But basically, it's a device that stores charge, and simplistically, two parallel plates produce a capacitor, a device that actually can store charge. We put a voltage source or power supply across these plates, and if we move charges from one to the other, which is what the power supply does, the positive charge is moving around like this, whatever positive charge goes on this plate is at the expense of removing those positive charges from this plate, and therefore you have the opposite, equal and opposite charges in these two plates. Now, in a similar way, we could say negatives are moving around the other way. And in any case, this charge separation that results on these plates produces an electric field. And that's the important thing, that there's an electric field there as a result of the charge buildup on the plates, and they're equal and opposite. So the power supply forces, it's not a very technically correct way to say it, but it's good enough for now. It's an electric field is really what puts forces on charges, so produces an electric field across there. But the power supply is responsible for that. The flow of charge can be thought of negative charges counterclockwise or positive charges clockwise. And you get this effect of this charge separation. Now, for a capacitor, which is this device, the quantity of charge that you get on the plates, probably surprisingly, if you think of this as a pump or like a kind of a pressure pump for water, but it's a pressure pump for charges, then the charges on the plate is proportional to how much voltage or potential difference there is across there. So that's pretty good. So Q turns out to be equal to the size of the capacitor times the voltage. So the bigger capacitor, more plate area, for instance, you have more charge at a given voltage, but more voltage, and you get more charge separated on those plates. Now this C is, just to be clear, it's a proportionality constant, really, and it's called the capacitance. So that's what the C is. And we can define C now functionally in terms of the charge and the volts by just being Q over V. So that ratio gives you the capacity of the capacitor. And the units are coulombs per volt, which has its own special symbol and definition, namely the farad, or F. So now we have this capacitor, and we need to push charges from one plate to the other. Do they want to just go by themselves? Well, no. When you separate charges, they want to come back to each other. So it takes work to do that. You can't do it effortlessly. So as you separate those charges, they want to come back more and more strongly all the time. There's a greater tendency, a desire to equalize the more charge separation occurs. So the work required to charge the capacitor, you probably aren't too surprised. It's a conservative force, and therefore it's going to be the potential energy that ends up getting stored in the capacitor. And that work, by definition, work equals Q times V, right? Charge times volts. Now that's to move charge Q across the potential V. Now, the thing is, this V across the capacitor is not a constant. It increases as the charge increases, so it's proportional to the charge. Hope that makes sense. In other words, as the charge separation increases, there's a greater voltage required to enable that to happen. So they're related proportionally. So as the capacitor charges, the V just keeps going up and up. So let's look at a graph of this. So the potential across the capacitor, as you keep putting charge in, the voltage goes up uniformly until you end up with the maximum charge that you can have in the capacitor based on the voltage of the power source itself. So it's a straight line relationship. It's really the same idea we had for the spring mass system. When we applied a force to the spring, this was force and this is X or stretch, and there was the same kind of relationship between them. Force increased linearly with compression or stretch. So the average force was half of the maximum. In like manner, the average potential here is half the maximum. So it's half the max. You can see that. We can put that right there. Constant value. So the work really to charge the capacitor is 1/2 the Q, which is the maximum charge in the capacitor, times the maximum voltage. So half of that. All right. And therefore, we have a little relationship here. We can say the potential energy in the capacitor itself is 1/2 Q times V. And we can utilize the relationships between Q, V, and C, the charge, the volts, the capacitance, to get a couple other forms. Let's do that. 1/2 QV is 1/2 Q is CV. CV is Q times V. 1/2 CV squared. Aha, remember the spring mass system? 1/2 KX squared. Oh, 1/2 MV, velocity, squared. Yes, similar ideas. Then we also have 1/2 C. V is Q over C, so Q squared over C squared. 1/2 Q squared over C. Quick example. The flash of a camera. Now back in the day, we had disposable cameras, and you can pull them apart and see the capacitor. But this is similar even now to a regular camera that takes a flash. Not your smartphone that has a little light on there. It's typically probably a little bit less. It's a little bit hard to contain a really super bright flash in the current technology of a smartphone in the 20 teens here. But let's say the flash unit stores energy in 150 microfarads and it's 200 volts. Well, how much energy can be stored in that capacitor at that voltage? 1/2 CV squared. 1/2 of C, there's the C, the V squared, 3 joules. So that's approximate order of the energy in the flash when you see a camera taking a picture in the dark. Well, that will kind of conclude the essential elements in electrostatics and potential energy, electric potential energy, electric potential, capacitors, and let's wrap up at this moment and have a wonderful day.